You write a simple SQL statement. Here I'm selecting a few columns from a product table, and the way these rows will be returned is not guaranteed to be in any particular meaningful order. But we often want to impose an order, like sorting the results by lowest price to highest price, or by highest to lowest, or by which ones have the best ratings, or the newest to oldest. And we do this by adding another piece to our SQL query, and this goes at the end after the where clause. And I'll add order by, and it's written as two separate words. And we say what column we want to use to order or sort our results. I'll use the column list price. Now, by default, when you use order by, it will sort results in ascending order. So here we're going to see the row with the smallest value first. If I just wanted to sort them the other way around, this needs to be in descending order. We would type in the word desk, D-E-S-C, afterwards. Now, if you want to be explicit, you can write ASC to say ascending order, but ascending order is the default behavior. You can also order using multiple columns. Let's say we have a large employees table, and I could order by last name, comma, first name. This is going to order the results first by the ascending last name order, and when there are multiple rows that have the same last name, then within that it will order those rows by ascending first name. So whatever sequence you write the columns after you write order by, it's going to use that to sort the results. Select these columns from that table where that condition is true. Sometimes the results we want is the actual data. We want all the different values and all the different columns for all those rows, but often we're not actually interested in the individual pieces of data. We want to summarize it in some way, like wanting to know how many orders did we get last month? Or what's the average amount that a new customer spends for their first purchase? What is the single largest transaction last year? What was the total revenue for sales of all products in the electronics category? And we can do this within our SQL using something called aggregate functions. There's a few new SQL keywords. Now think of the term aggregate here the same way that it's used in a phrase like an aggregate score in sports. It's just a way to combine the score from multiple matches into one single summarized result. And in SQL, an aggregate function is similar. We're going to take multiple values from the database, that could be just a few, could be hundreds or thousands, and then perform a calculation on all those values to get it down to a single value. Like, I want to know the total of something, or I want the average of something, or I want to know the largest value or the smallest value of all of these. So first example, we've seen how to do a simple select statement like select star from employee. And this will return everything, all columns, all rows, whether there's 5 employee rows or 5,000 or 27,521. But what if that number is what I'm actually interested in? I don't want to actually see all the data in all those rows. I just want to know how many rows are in that table. Well, I can use the aggregate function called count. And I write count and then a pair of parentheses, and we use parentheses with aggregate functions to always provide a little bit of extra information. Now here, I just want a count of everything, all the rows. So I'll use the asterisk. Now if I run this, the result is just a single number, a count of all the rows. And we can also use a where clause. Say I wanted to count the number of employees where salary greater than 50,000. And now we get that count. Count is a form of addition. We're just adding up the number of rows, but there's another kind of addition we'd often want, which is instead of counting the number of rows, we actually want to add up all the values in a specific column to get some kind of total. And we do that with the aggregate function sum. Now, this is, of course, very useful with any kind of financial data, totaling up orders, prices, revenue, etc. But we can use it with any kind of numeric information. Let's say I'm working with an online learning platform where we track the view time of users whenever they log on and watch a video, and where that's being stored in a table called user session. Now I could get all the individual information for a particular user with some SQL like this, just using a particular user ID. But if I just wanted to know the total amount of view time that this user has done over potentially hundreds of sessions, I could use sum. Now this time I don't use the asterisk inside the parentheses because I want the sum of only one column in particular. I want the sum of minutes watched. Now this is now going to find all the rows with this user ID. It will calculate the sum of all the values in the minutes watched column and then return that single result. So let's see another. We have a products table here, and I just want to know the most expensive product. Now, one way I could have done this is using order by list price descending, so the most expensive product would be the first result, but I'd still end up with all this extra data that I don't need. I could simplify this with the aggregate function max. Just find the maximum value of this column. Again, here I don't use the asterisk inside the parentheses. I'm interested in the maximum value of one specific column. This will now scan the table for this information and just return that single value. Now, if we have max, you might also make a guess that we're going to have min, and yes, we certainly do. We can select the minimum list price from product. We also have AVG for average. This will add up all the values in the list price column, divide by the number of rows, and return that single result, the average list price. Now, some database management systems have additional aggregate functions, like functions to calculate standard deviation, but the five that we've just covered, count, sum, min, max, and average, are by far the most common, and they're going to take care of a great deal of what you need to do in SQL. This, where you select count, comma, category from products. Now, you can write this, it just won't give you what you want. Depending on your DBMS, you might get an error or a warning. What's more likely is you're going to get results that aren't that meaningful. Because right now, this statement is a little ambiguous. It's confusing. It's like we're saying to the database, I want a count of everything and a category. So what you're going to get is a count of all of the rows together with one random category value. What we need to do is tell the database that we want to divide and group the results based on the values in that category column. And we do this using another SQL keyword, group by. This goes after the from, it goes after any where clause, but once I add this, I'll now get the results I was looking for. This is a count of how many products are in each category. So we're finding all the rows with identical values in the category column, grouping those rows and collapsing it down to one single result. So this statement is using both that aggregate function count as well as group by. And I'm pointing this out because it is typical. When you use group by, you will also use an aggregate function. Let me say that again. When you use group by, you also use an aggregate function like count or sum, min, max, average. And that's because we only use group by if you want some kind of summarization. We want to gather all the rows with identical values in a specific column, like saying, I want to count the products grouped by category, but it could be, I want a sum of the total sales grouped by region, or the average salary grouped by department, or to count the number of customers grouped by country, but where you get one result per group. And I stress this point because a very common mistake when people are new to SQL is they use group by when what they really needed was the simpler order by. For example, if I had simply wanted a list of all products, but where those products showed up in the categories they're in, so first are all the different books, then all the different clothing products, then all the different electronics products, it's easy to think, well, maybe that's a group by category, but it isn't. That's just order by category, because group by will not give you all the individual rows in the group. It gives you one result per group. Group by is intended to summarize. It is incredibly useful, but we use it together with an aggregate function, some kind of calculation. Group by is the ideal option when you want to break the results into groups and then perform some kind of calculation on each group. So I have a query here that will find all products where the status is not equal to discontinued. It will then group them by category and then give me a count of the number of rows for each category. And this works fine. We're using group by to get a separate count of how many products are in each category. However, one challenge you often run into with group by is if you ever want to use any of this calculated information, in this case, the count of the number of rows, as a way to filter the data itself. Here's what I mean. So let's say we've got these results. I look at them and think the only results I really want are the product categories with more than 100 products. This doesn't seem like a difficult request because we're obviously calculating that information. We can see that number in the result. So I might first be tempted to add it as part of the where clause. Perhaps I'd write something like this, where status is not equal to discontinued and count of everything is greater than 100. But this will not work. It will give me an error. And the reason is when we execute any SQL statement, the where part of the statement, the place where we are filtering the data, that always happens before the group by, before any calculations are done. So when I run this, it uses the where clause to filter the data to products that aren't discontinued, and then it will group it by category, and then it will count each category. So even though we know we're doing that calculation, we're counting the products, we cannot use that calculation within the where clause because it hasn't happened yet. So what do? Well, luckily, we have another SQL keyword, having, which exists for this kind of problem because we can use it together with a group by, and it allows us to do kind of an additional filter based on calculated information. Now, to be clear, we don't always need to use having, but if we're going to use it, it's added after the group by, so we can kind of recognize these belong together. So here we're saying, I want to see the products grouped by category, but only those groups having a count of more than 100. And this works and we get the results that we want. Now, having can be very useful. When you see it, expect to see it using an aggregate function like count or sum or average, because we use having when we want to filter on some calculated data that we can't put in a where clause. Sometimes you need to exclude duplicate or repeating information from your results. Let's say we have a large international customer base. We're shipping all over the world, and we've just been asked for a list of all the different countries where our customers are based. Now, let's be clear on the request. We're not asking for a count of how many countries. We might want that later, but right now, I just want a list of those countries. I could begin with select country from customer, and we would get all the countries in no particular order. And there's a lot of duplicate entries. We can expect many of our customers are from the same country. Now, sure, I could change this to order by, and it would make it easier to scan, but I would still have to wade through the results and have a lot of duplicates. What I really want is to see the values from this country column, but with just one result per value. I don't want any duplicates. Now, one thing you might wonder is, could we use group by? And actually, yes, we could. This would give us the information we wanted because group by will always collapse rows with the same value down to one single result. However, if all we wanted was just this list of values, group by is kind of overkill. It's really for summarizing. It's used with an aggregate function most of the time. So even though this is okay, it would work, there is a cleaner way, a simpler way, because there's a specific SQL keyword that allows us to say, I want the values from this column, but I don't want any duplicates. And that keyword is distinct. We use it before the column name just in our select statement. So instead of select country from customer, it's select distinct country from customer. Scan all the values in the country column, but I don't want any duplicates, just a single distinct result for each unique value. Okay, I hate beginning a video with some clickbait phrase like, here's the secret, but, well, here's the secret to writing SQL queries. One of the most important things you can do before you type anything is just sit back from the keyboard and first try to describe the results you want in English in one sentence. Just describe the results you want from the database in English in one sentence. You can say it out loud, you can write it on paper or a whiteboard, Just don't worry about SQL syntax. Just use plain language. Now, the goal is still to be precise, be specific. Don't just say, well, I want some customer data. No, say exactly what data you need, any conditions, whether you want any of it summarized or grouped or sorted. Just do it in a way that would still make total sense to anyone who doesn't know SQL. For example, I want the name and email address of all customers who've placed an order for more than $100 within the last 48 hours in alphabetical order by last name. I'm being exact, I'm being specific, but I'm using plain language. Or I could say, we need to know the users who have subscriptions expiring in the next 15 days, including their name, email, type of subscription, and expiration date, ordered by expiration date. Or I want to know the products sold in the past month, including the quantity of each product sold and the total sales amount, sorted by that sales amount in descending order. Now, it doesn't have to be perfect, but if you can get to this kind of thing, it becomes so much easier to convert this into SQL than if you just begin with, okay, I need some customer data, and then trying to figure out what it is you're asking for as you're writing the select statement. But it's not just about using plain language. It's also important to do this in a single sentence, a single thought, even if it becomes a long, long sentence, because that's going to get you thinking the right way, in a way that's closer to how SQL works. And this is particularly important if you have any kind of programming background, because SQL works in a different way to most programming languages. Most popular general purpose languages, whether it's Python or Java, C#, Swift, Ruby, JavaScript, TypeScript, whatever, they're all considered imperative languages, sometimes called procedural languages. Now, what that means is when you write code in those languages, you have some result in mind. You have to think through and describe all the individual steps to achieve it. You have to describe the process. It's like writing an extremely detailed recipe. Open the refrigerator, find a 12-inch ribeye steak, take the steak out of the refrigerator, put the steak on a plate, close the refrigerator, let the steak sit at room temperature for 20 minutes, get a 12-inch cast iron skillet, place the skillet on the stove, turn the heat to high, wait 5 minutes, check the temperature. But SQL does not work like this. It is not an imperative language. SQL is what's called a declarative language. And what that means is in SQL, you do not describe the process, all the steps, all the little instructions. You just declare the results you want as precisely as you can, and then you let the database management system figure out how to do it. So if an imperative language is like being in the kitchen and micromanaging every single step that everybody's taking, a declarative language is you never set foot in the kitchen. You just sit back and say what you want. Like, I want a medium rare 12-ounce ribeye. However, if there's any ambiguity in your request, it is up to the kitchen how to deal with it. So if you want to be more precise about your results, you become more precise about the request. You might say something like, I want a grass-fed medium rare 12-ounce ribeye with a hint of rosemary, seared at a high temperature, rested for 5 minutes, with a glass of Screaming Eagle Cabernet Sauvignon. Okay, I'm having a little fun with the analogy, but the point is this. The better you get at being able to think through and precisely describe the results you want, the easier it becomes to write SQL. And it's not just about making the database understand you. It's about ensuring you understand exactly what it is you're asking for. A lot of the time, we want queries that don't just retrieve data from a single table, but can actually pull from multiple tables at the same time. Because in a relational database, we expect a lot of our data is connected, interrelated. There's some kind of relationship between many of our tables. And the most common kind of relationship we need to work with is a one-to-many, like having an employee table and a department table. One department can have many employees, but each employee works for one specific department. Or customer and order. One customer can create many orders, but every order is for one specific customer. Or products and reviews. One product can have many reviews, but every review is for one specific product. So we often need to include this kind of relationship in our query. Anytime when what you want from the database involves two or more entities, like saying, I want to know how many employees work in this department, or I want a list of all products that have more than 10 reviews, or I just want the email and phone number of the customer who placed this particular order. And we do this by joining the tables, and this involves a few new SQL keywords. So let's take employee and department. In my example database, there is a one-to-many relationship between them. They're linked by this department ID column. The department table contains information about each department. It has its name, a description, a location, etc. And here, department ID is the primary key. So every row in this table must have a unique value for department ID. If we're given a department ID of 5, that will take us to one and only one row. Over in the employee table, there is also a department ID column, but here this isn't the primary key. It's a foreign key, and it's not unique because we can have many different employees who work in the same department. So in this table, the database allows the same value in multiple rows because here the column exists to be a reference back over to the department table. So how do we read these together in SQL? Well, let's just begin with a basic query from one table, the employee table. So we get results here, but all I'm seeing is that department ID, that number. And I actually want the name of the department, but that information is only in the department table. So I will add the SQL keyword join and then the name of the department table. Now, this is only step one. Now I could write columns from both of these tables in my select statement. And the department table has a name column. It also has a location column. I'll add both of those. However, I now have a problem because this department ID column that was in my original query, that exists in both tables. So there's ambiguity. Are we asking for the department ID column from the employee table or the department ID column from the department table? Now, you might not think, well, does it matter that much? Not really, but still, this is part of my original query. I was asking for it from the employee table, so I'm going to say that's the one I meant. This column should come from the employee table. Now, there's a few ways I can do this. For now, I'm just going to prefix this column with the name of the employee table and a dot. So table name dot column name, employee dot department ID. Of all of the columns I'm asking for that are in that select statement, department ID is the only column that exists in both tables. I don't need to prefix any of the other columns. I could if I wanted to. Let's say I wanted to make it very clear about where each of these columns is coming from. I could prefix all of them, and it would be very obvious which columns are coming from the employee table, which columns are coming from the department table. I don't have to do that. I only need to prefix a column if there's any potential for misunderstanding. But we're missing one crucial piece. You see, I've said I want to join these tables to connect them, but I need to be explicit about how these tables are connected, how they're joined, what column connects them. For us, that is department ID. And we do this using the on keyword. We are joining these tables based on this column in the employee table is a reference to this column in the department table. So again, I'm prefixing the column names with the table names. And in case you're wondering, it doesn't matter which way round I wrote these. We just have to name the two specific columns we are using to join this together. And now this join makes sense. For each employee, it's finding the department ID. It's using that to get the name and location from the department table and showing that data. Now, because we're actually getting the department name and location, we don't really need to show the department ID anymore. We could remove it. We're still explicitly joining using that column. I don't have to show it in the results. So we use the join keyword between the two tables, and we use on to say exactly how they're related. Now, what we're doing here isn't just called a join, it's called an inner join. And I could even make that explicit by writing the SQL keyword inner. Now, this would not change the functionality at all. A join is the same as an inner join. Now, what this means is we're only going to show results where there's an exact match between both tables. Now, you might think, well, isn't that what we wanted? And yes, a lot of the time, an inner join is exactly what you want. But there are other kinds of join, and we're going to get to that. When we use the join keyword in SQL, it's the same as writing inner join. And in fact, some implementations of SQL, like in Microsoft Access, actually require that word. You can't just write join, you have to write inner join. So an inner join retrieves data from two tables, but only shows results when there is an exact match. So in this case, we were looking at every row in the employee table and using the value of the department ID column as a foreign key to the department table. But let's say that the employee table here was defined in a way that we don't have to have a value in department ID, where null is allowed here. Perhaps some employees are considered as floating. They don't belong to any one department. However, if we're doing an inner join, then any employee row with a null value in department ID will not show up in the results of this query, because an inner join only returns rows when there is a match between both tables. Now that might be okay. That might be what you want. The problem with doing an inner join is if we thought this query was going to return all the employees with department information where possible, but if they didn't have a department, we still wanted to see that employee information. That won't happen here. That won't happen with an inner join. We need an outer join, where we still get results from two tables. We still join them wherever there's a match, but we're saying if there's any rows in table A that don't match with table B, we still want to see those rows. And to do this, I will first change the word inner to outer. We're not done yet, because we actually have to say which of the two tables takes priority. Which table do we want all the results from, even if there's not a match? And it's a really simple way that we do this. Because the join keyword is always written between the names of two tables, there's a table on the left side of the word join and a table on the right side of the word join. The easiest way to say which one takes priority is simply to say, is it the table on the left or the table on the right? Well, I want everything from the employee table, even if they don't have a match to department. So I'll add the word left. We're now doing a left outer join. The table on the left takes priority. And now all of the employee rows are returned with department details if that's possible wherever a match exists. But if the employee doesn't have a department ID, we still see that employee information. Any extra department columns will be null for these values. Now, conversely, we could change left to right and do a right outer join, which will flip this around and prioritize the department table. So you might think, well, what's the impact of that? Well, let's imagine that for us, the department table has a few rows for departments that they don't have any employees that actually use that department ID. Again, with an inner join, you would never see those rows because there's no exact match. Doing a right outer join, I now say, show me all the rows where they match, but if there's any additional rows in the department table that don't match, still show me those rows as well. Now, a small point. Just as we don't actually need to write the word inner in SQL, you can just write join. It's the same as writing inner join. We also don't need the word outer, because if you write left join or right join, you're saying I am joining these tables and the table on the left side of the table on the right side takes priority. Well, that's what an outer join is. So you don't actually need to write outer. But I will say when I'm joining tables, I write the word inner and outer, even if they're not required. Now, finally, there is also a full outer join, which is the most inclusive, which would get all rows from both tables. It would still match them wherever possible, but it's going to provide any additional rows with null values where there isn't a match. Generally, you don't need a full outer join as often as you need a left or right one. It is more typical that you want to prioritize just one of the tables, but it's useful to know there is a full outer join if you need that. When you're first introduced to inner joins and outer joins, you learn that you have to use the on key. How are we joining these tables? What column in table A is linking to what column in table B? It's very common, though, at some point you'll wonder, well, hang on. Isn't this relationship actually defined in the database itself? If it's part of the schema, if we have a column that's defined as a primary key in one table and that same column defined as a foreign key in another table, why do we have to say in SQL how these tables are connected if that's already defined in the database? And it's a good question. There's a few answers, including, well, you actually don't always have to say how these tables are connected. We'll get to that. First, understand, the main reason we define the relationships in the database is for data integrity and consistency. It is not just to make it easier for us to write SQL. It is much more about maintaining the validity of the data. If you're adding a new order and you're saying this is for customer 742, the database will make sure there actually is a customer 742 before it lets us do that. But reason number two is the databases often contain quite complex relationship where a single table could have multiple relationships with other tables. And some relationships are very well defined, but some can be more informal, where perhaps the related columns might be named differently, or you need to join them based on some calculated information using dates or string values. So when you can specify the join conditions explicitly, it gives you a lot of control over exactly how those joins happen. However, having said all that, there is something in SQL called a natural join, where we use the keyword natural instead of inner. And a natural join doesn't require us to define the columns that we're joining on. It will automatically look at both tables on either side of the natural join keywords. And as long as they both have a column with exactly the same name and exactly the same data type, it will join the tables using that column. One issue is that not all DBMS systems support natural join syntax. For example, Microsoft SQL Server, IBM DB2, they don't use it. If the database you're using supports using natural join, and you know that the tables you're connecting have the same name and the same data type for those columns, then by all means use it. But if you know how to write inner joins and outer joins with explicit join conditions, that's something that's always useful across every relational database. Working with multiple tables in one SQL query, like when you're doing any kind of join, you often need to use the name of each table multiple times within that query when you're describing which columns are coming from which table, or where you're saying exactly what columns we're using to join them together. Now, a table alias allows us to provide a short, temporary name for those tables, essentially a nickname, and it makes it more concise, more readable within that query. So imagine we want to retrieve a list of orders together with some information about the customer who placed that order. So we're joining the orders table with the customer table to get things like the order ID, the name of the customer, the order date, and let's say both tables have a column called status, which can mean different things. There's a status of an order, which could be shipped or completed or canceled, and there's also a status of a customer, which could be active or inactive. So in this example SQL, I've used the full table name multiple times to make it obvious where each of the columns are coming from. I'm using the name of the orders table 8 different times. I'm using the customer table 6 times. So let's change this to use an alias. So use the full name of the table just once and the shorter alias the rest of the time. Now, it's very common to just use a single letter for each table. So we have the customers and orders table. I'll just use C and O. So after each table, a space and then that letter. From orders, space O, inner join customers, space C. Now, wherever else I was using the full name of this table, I could just replace that with that letter. While this isn't a massive transformation, it shortens the query. More importantly, it allows us to more easily focus on the column names. It still allows us to easily understand where each column is coming from, but the column names are more important. Now I'm using lowercase letters for each table name here. That's very common to see, but it is basically your own choice. You can use uppercase letters, multiple letters, whatever alias makes sense to you. Now, some people would argue that I'm missing an SQL keyword here, because when we're creating aliases, you can use the keyword as to make it very clear this is happening. Instead of just table name followed by the letter, it's table name as letter. So orders as O, customers as C. In most implementations of SQL, the keyword as is not required. Now, we can also create aliases for columns, not just tables, but that's another video. As your ability with SQL grows and you get better at this thought process of first describing what you want in a single sentence and then converting it to SQL, you are still going to run into a few situations where you can't quite figure out how to make that work. For example, let's say that the requirement I have is that I want to see all products where the list price is above average. This doesn't sound too hard, and there's nothing in this sentence that we haven't already done. I know how to write a query to ask for all products above a specific list price. I also know how to calculate an average using the aggregate function AVG. But if I try and combine these two ideas to select product information where the list price is above the average list price, I might try something like this. Unfortunately, this will not work. I'll get an error, and it's because of the way every SQL statement works. Whatever you write in the where clause, the conditions that you use to filter any data, that is always done before any calculations or aggregate functions are evaluated. Basically, you can't put an aggregate function like AVG directly inside as part of a where clause. So what do? Well, the clue here is that we already knew how to do the two different parts of this. Here's how we select rows above a certain price. Here's how we calculate an average. And anytime you're in this position where you think, I know how to write SQL to do this part of it, and I know how to write SQL to do this part, I just can't figure out how to combine the two, one of the options is what's called a subquery. And this basically means you write a query inside another query. It doesn't mean you write two SQL statements, one after the other. It really does mean one inside the other, like this. I'm going to take this first part where we're selecting products above a specific list price. And instead of the literal value 100, we don't want this fixed value here. I'll replace this with a pair of parentheses. And then I will just move my second query that calculates the average inside those parentheses. Now this is now a subquery. And notice I didn't change anything about this inner query. I didn't have to write it in some special, unique way. It is just a normal query. It would work by itself, but we're using the results of this inside another query. And when we run this entire piece of SQL, the subquery that's inside the parentheses will be evaluated first. It will work as if we'd written it by itself. It'll find the average list price at this moment. Of course, the average list price could be different from moment to moment or day to day based on whenever we've added new products or the price is changing, but it'll figure out the average at that moment. Let's say it's 47.24. The results will now be taken as if we'd written it directly inside the outer query. Find all products with a list price greater than 47.24, and we get what we wanted. All products where the list price is above the average. If we ran this again tomorrow, it would recalculate that average and do it again. Now, this is just one example, but subqueries are a very powerful technique in SQL, and they allow us to build complex queries in a more manageable and readable way. You're looking at the results of a standard query. The column names you get in the results set are just, well, the column names as they're defined in the database, and no surprise there. They're the columns we asked for. But sometimes it's useful to be able to change this name. Here's what I mean. Let's say we're retrieving some product inventory information from a table. The table is from some old legacy database with very short cryptic column names. We might know that these columns represent the name, product ID, the number of items in the inventory, and the item location, but somebody else looking at this data might have no idea what these two columns represent. So we could provide an alternative name, an alias in the output of the query to make it more readable, just to clarify it. And we use the as keyword after the columns we want to rename. So I'll write select nm as name. Item underscore inv is now items in stock. Item underscore lc is now location. I could have provided an alias for the ID. I just wanted to show you don't have to provide an alias for everything, just the columns you want to. I could even change the name of the column to include spaces, though I would need to include that in quotes to do this. But I want to be clear, this is not changing the database schema at all. It does not rename anything in the table. It is purely used for the output of this query, but it can still be very useful. Now, creating these aliases is also very handy if you're using any kind of calculated column, like using an aggregate function. So I have a query here to calculate the average list price of products grouped by category. But if all I see is the result, I might not know what this column represents. Is this the average price, or the maximum price, or the minimum price, or the total number of items? Who knows? Because the name that shows up for any calculated value, well, this can actually be different depending on the DBMS you're using. Some of them don't provide a name for this column at all. Some might call it column 1. Others might use the name of the aggregate function. But if we want to decide that ourselves, we could use as to provide an alias in the results. I take this aggregate function and say as average price. This now shows up with that column called average price. Again, we're not actually changing anything about the database structure or the definition of anything. It's simply using as to have more useful names in our results. Union operator in SQL is used to combine the results of two or more select statements into one larger result set. Now, union is a very simple keyword to use. You literally just write it between two valid select statements. What can be a challenge is recognizing when to use this. So here's an example. It's not unusual that in a large organization with a large database, you'll sometimes have separate tables that store very similar information, where those tables might have been kept apart due to organizational reasons or perhaps historical data. Let's say in the past we had used an older system to manage our customers, and now we have a new system. And we've ended up with two tables that store customer information. We have current customers and past customers. Now, these tables might have a similar schema, but it's not identical. There's some differences in the columns. So we didn't try and merge them together in the database, and that's okay. But now we just want a complete list of all customer emails, regardless of if they're current customers or past customers. And we could use union for this. I could write two select statements, each one getting the results from these different tables, and then I write union between them. And I'll end up with a single result set that combines data from both queries. And notice I don't have the semicolon after each of the queries. It's just once after this entire larger SQL statement. And the first question you might have is, do the columns have to have the same name in both tables? And no, they don't. If this column had been named differently between the tables, it would still work. However, in the results, it will use the name from the first query. Next, we can use queries that retrieve multiple columns, not just one, but here's the rules around that. If you're going to use union to combine the results of two queries, then both queries need to be bringing back the same number of columns and where the data types are compatible. If your first query is bringing back just an email address and the second query brings back a timestamp and a binary large object, it just doesn't make sense to try and combine those results, and you would get an error if you tried. With union, we expect that both of these queries are fetching similar data. They're fetching the same number of columns and where they have compatible data types. By default, one of the great things about union is it will also check the results and it will discard any duplicate values. So in this case, if the same email address existed in both the current customers table and the past customers table, you would only see it once in the results. However, this deduplication does have a performance impact, particularly if the tables are large and if the DBMS has to do a lot of work to scan all the results for any duplicates. So we don't have to do this. If you know that there aren't any duplicates between the tables, or you don't care if any duplicate results show up, or perhaps sometimes you might even want to see duplicates if you're trying to do deeper analysis of the data, you can turn the union into a union all. And that's the only difference. A regular union will do this deduplication of the results. A union all will not. But union all can be substantially quicker if you're dealing with a lot of data. Quick sidebar. A question I have sometimes had in the past is, so if I want to get information from two different tables, I know I can use join and I know I can use union, but how do I know when to use one over the other? And okay, it's true these are both SQL keywords that allow us to get information from multiple tables, but in any real-world situation, you rarely have to make a choice between them because the reason we use each of them is extremely different. We use a join when the tables represent different entities that have a relationship, like a customer table and an order table, or employee and department. And we join those tables with very different data. So every row could use some columns from table A and some columns from table B. But a union is not about relationships. Union is more useful when the tables have similar data. You want a bunch of rows in table A and a bunch of rows in table B, and it's just convenient to throw all the results into the same bucket. So with a join, we're getting more data, and you get it horizontally, more columns, because every row could have information from both table A and table B. With a union, you get more data vertically, more rows, where every row is either from table A or it's from table B. That's the difference. End sidebar. We've been focused on using select statements to retrieve information from a database, but that begs the question, how did the data get into the database to begin with? Well, let's first recognize that any computer system that deals with storing data, like a relational database, will typically need to provide four fundamental functions. Sometimes we use the acronym CRUD for this. We expect to be able to create, read, update, and delete. In SQL, read is covered by the select statement. We can create new data with the insert statement. And the last two actually match the letters in CRUD. So we update and we delete. So let's take insert first. To insert or add a new row of data into a particular table, the basic format is this. We say we're going to insert into, we give it a table name, and then a list of the columns we're inserting and the values we're inserting into those columns. We give the specific names of the columns we're providing values for, because you don't always need to provide data for every single column in a new row. The table might be defined so that some of the columns provide default values, like automatically generating a primary key. Other columns might allow null. Columns and values must match in their number and their order and their type. So you can't say that you're going to provide 5 columns and then only provide values for 4 of them. Also, the data types have to be consistent. If a column is defined in the table as an integer, you can't then try and insert a string value into that column. So let's say we have a basic employee table that's been defined in such a way that the employee ID column is automatically generated. It will increment for every new row. Perhaps one of the other columns is defined with a default value. So if we don't provide a value for this column, it'll be set to general. So we can then write a valid insert statement providing values for the other named columns. So when we execute this statement, we have a new row created with an automatic new employee ID and an automatic value for the department column. Now, we could also insert multiple rows at the same time by providing multiple sets of values, each within their own set of parentheses. To be clear, you certainly don't expect to manually write insert statements for every new row in a database. It is much more likely that these will be done programmatically using some kind of application or perhaps some kind of bulk upload. But this is the kind of insert statement that will be actually going on behind the scenes. If we have data in a table, we'll sometimes need to change the data and update the values in the columns of a particular row. And we use the update statement for that. And the same way that a basic select statement has 3 parts to it, that we select specific columns from a specific table where some condition is true, we also have 3 parts to any update. We update a specific table and then set one or more columns to a new value where some condition is true. An example here, we're updating the employee table and we'll set the status column equals to retired where the employee ID equals 6543. Now, if you want to update multiple column values at the same time, you certainly can. You just separate those with commas. Now, technically, you are not required to have a where clause in an update statement. But if I ever see an update statement without a where clause, I will instantly assume that's a mistake and a potential disaster waiting to happen, because leaving off the where clause in an update statement means you're telling the database, change this column value for every single row in the table. Very occasionally, that might be what you want to do in an update, but more often you want to restrict your updates to just one row or a handful of rows. So that's why we would need and would expect a where clause. And using where in an update is exactly the same as in a select statement. Now, most issues around updating data go back to data integrity. So if a column is defined in the database as an integer, you're going to get an error if you try and update it with a string value. And if a column is configured as a foreign key into another table, then the database is going to make sure that any value you change is a valid reference before it will allow you to do that. The delete statement in SQL is actually one of the simplest of any of them because it's all about the where. And we use the keyword delete along with from to say which table we want to delete rows from. But unlike the inserts or updates and selects, when you use delete, you don't name any specific columns in the table. In fact, you can't name any specific columns because delete always affects entire rows. If you delete anything, you're deleting at least one entire row. You can't delete part of a row. So the where clause in a delete is the most important piece. This is how you control which row or which rows in the table you're going to delete. And you can delete multiple rows at a time, the same way that you could use a where clause in a select that would select multiple rows at a time. The main point with delete statements is be careful. Almost everyone who's worked with databases for a while has some horror story about a delete statement that was written a little bit too quickly, a little bit too casually. Because here's the thing. If I accidentally left out the where clause and I just wrote something like delete from employee, if I execute this SQL, the database may just say, well, you're the boss, and delete every single row in the employee table. It's not going to ask, are you sure? It's not going to require any kind of confirmation. It will just do it. Delete is a very, very powerful keyword. Some database management systems have a safe mode where every delete statement is required to have a where clause, and that where clause must even use a primary key, but don't count on this to make sure that you don't make any mistakes. And a very good practice when you're working with deletes and also when you're working with updates is first create the statement as a select to make sure that the where clause that you've written is only going to return exactly the rows you expected and only affect those rows. Confirm that before you then turn it into a delete or an update. Of all the SQL statements you'll ever write, the majority of them will begin with the word select, followed by perhaps inserts, updates, deletes. Now, these are sometimes described as the DML part of SQL. DML stands for Data Manipulation Language. But let me be clear, this term DML sounds official and important. It really isn't. In fact, the main reason I even mention it is you'll sometimes see this in documentation or even job listings.
We're looking for strong SQL skills, including data manipulation language, DML, and data definition language, DDL.
It kind of sounds like something separate to SQL. It isn't. DML is simply a convenient word to describe that part of the SQL language that deals with reading and manipulating the actual data in a database. So select statements, inserts, updates, deletes, and all the other keywords we use along with those, like from, where, group by, order by, join, etc., etc. But you might think, well, if all that stuff is considered a part of SQL, does that mean there are other parts of SQL? And yes, there are other parts to this language. You can think of SQL as kind of subdivided into a few different areas, and it's because there are other tasks and goals we can have when using it. Think of it like this. If you have a car, it is one set of skills to know how to drive, and that's the skill that most people want to know. But it's a completely different set of skills to be a mechanic. We've been focused on driving. We're using SQL to work with the data in an existing database, how to retrieve that data and sort it, summarize it, group the results, update it, delete it, and so on. But sometimes we might need to switch into kind of a mechanic mode. We want to go under the hood. We want to affect the structure of the database itself to perhaps create a new database, or change the definition of a table, or define the columns that exist, or configure primary keys and relationships. And all of that can also be done with SQL. It's a part of the language that's sometimes called DDL, or data definition language. And that mostly just comes down to three new SQL keywords: create, alter, and drop. We use create to create new databases and create new tables. We use alter to change them, and we use drop to get rid of them. So here's an example of a create table statement. We're creating a new table called employees with 5 columns. Employee ID is an integer. It's also the primary key. First name and last name are both variable length text or character strings with a maximum of 50. Email is also variable length text, but it could be 100 characters long. And finally, hire date is a date. A very simple example here. But if later we realized we needed an additional column on this table, I could use the SQL keyword alter to do that, to alter the table employees and then add a column department ID, which is an integer. Now, finally, we could even get rid of the table completely, just drop table employees. We don't use the term delete for doing this because we already have the delete keyword, which deletes rows of data from a table. We do not want to use the same keyword that might completely delete an entire table or even entire database. Here's the thing. I am intentionally just showing these as a bit of exposure. I am not spending time exploring the syntax of these for a few reasons. First, because the real work of creating new databases and new tables is not the SQL to do it. That's the easy part. That takes a few minutes. The real work is all the significant planning and database design that needs to happen before you write any of those statements. And that's about understanding the business rules. It's about ideas like data normalization and indexing, and even the specific DBMS software that you're using. And none of that is stuff we're covering here, because this is an introduction to SQL. It is not a database design course. Also, even the people who do work on the actual database design and affect the structure of the database, well, they often find it easier to use an application like MySQL Workbench, SQL Server Management Studio, rather than creating hundreds of create and alter statements. So someone who is a database administrator might spend a lot of time with these keywords like create and alter, but most software developers don't. Most data analysts don't. They spend their time dealing with the actual data in the database, not changing the definition of the database. And there's even another area of SQL called DCL, or Data Control Language, and that deals with access control, meaning permissions and security, like which users are allowed to access the tables in this database. And can they use all of the tables or just some of them? And if a user has access to a particular table, can they just read the data? Could they also change it or delete it or add new data? Are they allowed to redefine the structure of the database itself? So all of these kinds of things can be configured separately. And we use SQL keywords like grant and revoke. But again, I'm not going to get into these keywords here because that is very much a database administration task. So if you ever hear these terms, DML, DDL, DCL, just understand them as there are some SQL keywords we use when we're dealing with the actual data in a database. There are a different set of SQL keywords to change the structure of the database, and another set of SQL keywords to affect the security, permissions, and access control of a database. And they are worth considering as almost separate from each other because often it isn't even the same people that are doing these tasks. In any large enterprise level organization, you might have hundreds or thousands of people that can write SQL to query a database, but where hardly any of them have the permissions to change the definition of the database or affect the security of it, those tasks, those responsibilities are restricted to a much smaller set of people with a different set of skills. And we've been focused here on this DML area of SQL because, as I said at the very beginning, this is what most people need to do with SQL most of the time. Once you have a foundational understanding of SQL, a useful technique that's available to us now is the option to use generative AI tools like ChatGPT, Google Gemini, or Anthropic Claude. Now, if you're a software developer, you may already be using AI-driven development tools like GitHub Copilot, but even the general purpose AI tools are getting very good at this. Now, I'm certainly not going to suggest something oversimplistic like, well, just get generative AI to write all the SQL for you. That's not going to work out very well. You see, if you're using a general purpose AI tool, well, first, it doesn't understand your database schema, any of your relationships, or your data. And okay, you could tell it about those things. You could explain the schema of your tables, but first, the organization's probably going to frown upon uploading sensitive data into a generally available AI tool. But also, it's not necessary to do this. We can still get a lot of value from it. We want to use AI as an assistant, as a helper. Yes, it can help with SQL syntax, but it can also help you understand and reinforce what you've already learned. But you still have to provide direction. You still have to critically review everything the AI suggests. Here's a few examples of how we could use it. Now, first, let's go back to this idea of, can you describe what you want from the database in English in one sentence? Like saying, I want to know the products sold in the past month, including the quantity of each product sold and the total sales amount, and sort it by the sales amount in descending order. Because you could ask generative AI to provide a hypothetical SQL example for this description. You've defined it in plain English, you get it to give you the SQL, and it will come up with its own table and column names. I'm going to strongly suggest you don't just ask the generative AI to just provide the SQL. You also ask it to explain step by step and use those words, because it's then going to break down the choices that it makes and why it's making those choices, which not only will help you understand and map this across to your own situation, but it's also going to allow you to recognize if generative AI has misunderstood anything, if it's gone off the rails. But this can also be a great way to remind yourself of fundamental concepts that we've explored here, like saying, just give me an example in SQL of using group by versus order by. Or perhaps, in SQL, are there performance implications for doing a wildcard search? Short answer, yes, there are, and here's why. If you're having issues with your SQL, it can help you debug. And this does not mean you have to copy and paste your entire SQL query into ChatGPT. You could do that, but again, many organizations will frown on it. Let's just say you've written some SQL, you're getting an error on one particular line whenever you try and execute it. You know that it's complaining about your where clause. So you might just say, I'm getting an error when I try and use an SQL count function in my where clause. Why? And it's going to tell you, well, first, you can't use an aggregate function in a where clause. Second, here's an explanation of why. And finally, here's what you can do instead. And you can even flip this relationship around. Instead of you asking the AI some questions, get the AI to ask you questions and check your understanding. Ask me a few questions about SQL inner joins versus outer joins and validate that you actually understand what these are. And okay, we could go further, but beginning with these 4 basic situations is incredibly helpful. Ask the AI to provide sample queries for specific problems that you can describe in English. Use it to review core SQL concepts. Help identify where things went wrong in your query by using either specific error messages or situations, and also get it to ask you questions to check and validate your own knowledge. But notice that with all of these approaches, it still benefits us. We're not asking the AI to replace us. We're not removing ourselves from the picture. We're using AI to extend and build on what we understand. So we're adding to and reinforcing our own skill set. My goal with this course was to keep it very focused on SQL and not about a particular DBMS or vendor. But to take this further, well, yes, at some point you need to choose and use a specific database or specific application if you haven't already done that. Now, if you currently have access to a database, the easy answer is you just begin with that one, whether that's MySQL or SQL Server, PostgreSQL, or any other relational DBMS. Now, if your organization already has a data analysis platform that has any kind of sandbox you could use for experimentation, then dive into that. If you're so inclined, you could install a local database on your own machine to have your own system to experiment with. I'm not going to make a strong recommendation for any particular DBMS, but if I'm looking at cross-platform options you could install on Windows or macOS or Linux, the simplest one is SQLite, sometimes called SQLite. This does not have the robust features of more advanced DBMS systems, and it isn't trying to have all those advanced features. It doesn't need to. It's still useful for testing and experimentation of regular SQL. Beyond that, there are options like MySQL Community Edition or PostgreSQL, which is open source and free to use. If you're on Windows, there's Microsoft SQL Server Express and Developer Editions. These are both free. You can install them on your own Windows machine. Most of the vendors also have sample databases you can download and install locally. They'll give you a bunch of tables with predefined relationships full of sample data you could use to write some SQL, test your queries, and just experiment without worrying about messing anything up. Now, are there more SQL keywords you're going to encounter? Absolutely. But still, you're going to find the majority of queries use what we've covered here in this course. But I'm going to end with something I have said a few times now. That first, try and describe what you want from the database in plain language in a single sentence, because the most important part of getting comfortable with SQL is making sure you understand exactly what it is you're asking for before you try and write it in SQL. And the better you get at thinking through and articulating that in normal language, the easier it becomes to write SQL. Hope you enjoyed the course. Thanks for joining me, and I'll see you next time.